Good day, students. I hope all of you are safe. In the previous lecture, we discussed some methods to handle deadlocks. We discussed that there are at least three broader ways through which deadlocks can be handled in a system. They include prevention, avoidance, and recovery. By prevention, we mean that out of the four necessary conditions for a deadlock, at least one of those conditions does not hold. We discussed that there are four conditions. If all of them hold simultaneously in a system, we have a state of deadlock. However, in prevention, we ensure that at least one of them does not hold to prevent the deadlock altogether. In the avoidance method, we ensure that the system never enters into an unsafe state. And by this unsafe state, we mean that there is no possibility of a deadlock. We discussed that if we have single instance of resources, then we can use the resource allocation graph for avoiding this deadlock. However, if we have multiple instances of a resource type, then this resource allocation graph may not be very useful, so we have to opt some other mechanism. We discussed that that mechanism could be the banker's algorithm, and we will discuss it in today's lecture. Also in today's lecture, we will discuss the third method to handle deadlock, that is to recover from it. So we let the deadlock occur in the system, then we detect it, and then we recover from it. So here we have two methods to avoid deadlock in a system. The first one in the presence of single instance of a resource type, that is resource allocation graph. We discussed it last time. Today we will see how we can avoid the deadlock in the presence of multiple instances of a resource type and how we can use the banker's algorithm for this purpose. So banker's algorithm works on multiple instances of a resource type. When a new process enters into the system, it declares the maximum number of resources that it will require throughout its execution. So once a process requests a resource, the system determines how many resources it has in the system, and once this allocation is being granted to this process, whether the system will remain in the safe state or not. If the system remains in the safe state, this request is granted. If this request or allocation leads the system into an unsafe state, the request is declined. So resources are allocated only if the system remains in the safe state. If the system can lead to an unsafe state by this allocation, the request is declined for the moment and the process is asked to wait unless some other resources are returned by other processes. Once a process gets all the resources that it requires, it completes its execution, and once it completes its execution, it may return all the resources that were allocated to it previously. And that is how we regain all the resources and then we can allocate them to other processes that are present in a system. Before moving with the banker's algorithm, let's have an example that will elaborate on its working. We will use this example side by side with the algorithm to enhance the understanding about the working of this algorithm. So in this example, we have 5 processes from P0 to P4, and we have 3 resource types, A, B, and C. As you know that Banker's algorithm works on multiple instances of a resource type. So in this example, we have 10 instances of resource type A, 5 instances of resource type B, and 7 instances of resource type C. So we know that in this algorithm, there is a requirement that when a process enters into the system, it has to declare the maximum instances of the resources that it will require throughout its execution. So in this case, P node would declare 7 instances of resource type A, 5 instances of resource type B, and 3 instances of resource type C. Likewise, we have P1, 3 instances of resource type A, 2 instances of resource type B, and 2 instances of resource type C. So likewise, these numbers reflect different instances of these 3 resource types. So at any given time, these are the allocated resources. So at any point in time, P node already has 0 instance of A, 1 instance of B, and 0 instance of C. So this matrix provides us the number of instances of each resource type that is already being allocated to these processes. So now, after having the maximum and allocated resources, we compute the total number of resources that are left with the system. So at this time, we have 3 instances of resource A, 3 instances of resource B, and 2 instances of resource C. And this number can easily be achieved, as we know that at the beginning we had 10 A's, 5 B's, and 7 C's. So if we just add these numbers together, we will get the number of available resources at this moment. So in the allocation, we have 2, 3, and 2 A's, which is 7. So we have 7 resources allocated out of 10 A's. So we are left with 3 instances. Just like with B, we have 1 plus 1, that is 2 instances, which will leave us with 3 instances of B still available in the system. Likewise with C, we have 2 plus 1 plus 2, 5. So in the system we have still 2 resources available for this. So we have 3 things when we are dealing with this Banker's algorithm. The first one is number of processes. Then we have the resource types and their instances. And then we have these matrices. The first one is the maximum resources and their instances that are required by each process. The second one is the allocated resources at any given time. And the third one is available resources that are available with the system at any given time. Over here, we have the data structures as presented in the Banker's algorithm. So you can see that they are almost the same as we had in the previous example. So the first matrix, a 2-dimensional array, is the maximum matrix. Now that is used to store the maximum instances of each resource type provided by each process. Now you can see that this matrix is populated when processes enter into the system, as the processes have to declare the maximum requirement before they start their execution. The second matrix, another 2-dimensional array, is the allocation matrix that stores the number of instances per resource type against each process at any given time. So these are the number of allocated resources at any point in time. The third one is a single dimensional array that stores different instances of each resource type currently available in the system. So all the instances that are still available with the system are stored in this array. And using these two-dimensional arrays, the maximum and allocation, we get another matrix that is the need matrix. This is another two-dimensional array that is used to store the current need of each process that is present in the system. So you can see that if we have the maximum requirement of a process and we have the maximum number of allocated resources, we can compute the current need for each of these processes. So for instance, if a process requires 10 instances of a resource type and 3 are already allocated, so we know that the current need will be 7 instances of that resource type. Over here, we again have the very same data structures. So the first one is the max data structure. Then we have the allocation data structure. Then we have the available data structure. And from this maximum and allocation, we can generate in another matrix, that is the need matrix, by subtracting allocation from the maximum matrix. So you can see that for P naught, the maximum requirements were 7, 5, and 3. 7 instances of A, 5 instances of B, and 3 instances of C. And if these instances were allocated to process P naught, then we can see that the need matrix will be 7 minus 0 will be 7, 5 minus 1 will be 4, and 3 minus 0 will be 3. So this need matrix is populated by subtracting this allocation out of this max matrix. The banker's algorithm has two major components. The first one is safety algorithm and the second one is resource request algorithm. This safety algorithm component is used to verify whether the system is in the safe state, while the resource request algorithm component verifies that after various modifications of different data structures, what will be the current state of the system. This safety algorithm is utilized quite often, even independently before the system starts executing and after every allocation of resources. So the working of this safety algorithm is quite straightforward. So we have the matrix of available resources, the resources that are present in the system. So we find out some process where the need of the process is less than the available resources in the system. So only one component. Do we have a process having less requirement or less value in the need matrix than the available? If we have some process that satisfies this criteria, then we allocate those resources to it and we can assume that this process has completed its execution. And then we move on to all the other processes one by one and verifying every time that their need matrix is less than the available resources in the system. And once we can find a sequence of processes that can complete their execution in the current availability, we declare the system in the safe state. The second component of Banker's algorithm is the resource request algorithm. So in this component, we check whether a particular request of a process can be allocated or not. And how we check it? The process is not that difficult. It is quite similar to the safety algorithm. So first of all, we check whether the request can be handled within the available resources. If the answer is yes, then we subtract the request from the available resources and put it into the allocated. So we assume that the request is being allocated. So resources from the available matrix will move from the available to the allocated. And uh, once we have the modified values of the data structures, then we move on to computing whether the system is still in the safe state or not after the deduction. If the system is still in the safe state, we can allocate the resources. However, if we could not find a sequence through the safety algorithm that the system may not in the safe state, then we decline this particular request, and we still keep on finding sequence through the safety algorithm when we have a safe sequence where the system will remain in the safe state. So now let's have this through the example. So over here we have all of these data structures. So we have the maximum data structure, we have the allocated resources, we have the available resources, and now we have the need matrix as well. So now let's verify, let's compute the safety of this system. So first of all, can we find some process where the need is less than the available? So let's check. P naught has a lead which is greater than the available, so we cannot take P naught. Moving on to P1. Yes, the need of P1 is less than the available resources. So the resources that are required by P1 will be deducted from the available resources. Now, as you can see that the need will become 0 and these resources are reduced from the available resources. After taking them from the available, they will be added to the allocated resources. So you can see that 122, one instance of A, two instances of B, and two instances of C will be taken from the available resources and added to the allocated resources. Now, once the allocated resources meet the maximum resources, then we can assume that the resources required by P1 are already allocated to it and P1 can complete its execution without any further delay. So we can safely assume that P1 completes its execution and leaves the system. However, before leaving the system, P1 will return all the resources that were already allocated to it. So now we have these resources present in the system. So you can see that 210 were the resources that were available before P1 returned its allocated resources. Now these 3, 2 and 2 resources when will be added to the available resources will make the whole sum as 5, 3, 2, and P1 has already completed its execution. Moving on, do we have any other process that can complete its execution within these available resources? So let's look for P2. As you can see that P2 requires 6 instances of resource A which are not available. So we move on to the next process, which is P3. So you can see that P3 can complete its execution within these available resources. So we will pick up P3 as the next process. Now these resources will be taken from the available. So you can see that the new available will become 5, 2 and 1, while they will be deducted from the need because now they are already allocated to it. After having this reduced from the available and making this need as 0, we will add it to the allocation. Now the new allocation for P3 becomes 2, 2 and 2. So now as you can see that the allocated resources are equal to the maximum required resources. So we can safely assume that P3 can complete its execution within these resources. So we assume that P3 has completed its execution and will return the allocated resources back to the system. So now in the system we have 7, 4 and 3 instances of A, B and C resource types. Now by looking at this system, now we have successfully executed P1 and P3 and now we have new available as 7, 4 and 3. Now, by having these resources, can we find any other process that can complete its execution within these resources? So we can see that P4 has requirement which is less than the available resources. So we will allocate the required resources of P4 to it and we will remove it from the system and give it to the process P4. So first of all, these resources are reduced from the system. The need becomes 0 and now it will be added to the allocated resources of process P4. Now the allocated resources for P4 become 4, 3, 3, which is equal to the maximum resource requirement for this process. Now we can assume that P4 can also complete its execution within these allocated resources, and once it completes its execution it can return back all the allocated resources to the system. So the new state will become 7, 4, 5 instances of resources A, B and C respectively. Also by having these resources, now we have P1, P3 and P4 already completed their execution. Again, at this stage we have to find out some process that can complete its execution within the available resources. Now starting from P0, do we have available resources greater than 7, 4, 3? Yes, this time we do have these resources available to us. So we will pick up P0 as the next process to execute. Now these resources will be deducted from the available matrix as well as the need will become 0 and now they will be added to the allocation array for P0. Now as P0 has all the resources that it requires to complete its execution, we can assume that it can complete its execution without any further delay. So once P0 completes its execution, it can return all the allocated resources back to the system. Now P0 has completed its execution and has returned all the allocated resources back to the system. Moving on, do we have any process that can complete its execution within the available resources? This time the only process that we have in the system is P2 and again it can complete its execution within the available resources. So we will pick P2 as the next process to execute. Now all the resources required by P2 are taken from the system and the need matrix also becomes 0. Now these resources that are taken out from the system will be added to P2. Now as P2 has all the resources that are required to complete its execution, we can assume that P2 will complete its execution without any further delay. And once it completes its execution, it will return back all the allocated resources to the system. Now, this is the new state of all the data structures after the execution of all of the processes. Now you can see that the available resources are 10 instances of resource type A, 5 instances of resource type B, and 7 instances of resource type C, which were the actual resources when we started the execution of all of these processes. Also, as we have found a sequence of processes that can complete their execution within the available resources, it means that the system is in the safe state. Now, after analyzing that the system is in the safe state, let's do an exercise. What if process P1 requests for 1, 0, and 2 instances of resources A, B, and C respectively? So if the current availability of resources is 3, 3, 2, what will be the new state of the system after this request is granted? So you have to compute the new availability of resources, and then you have to find whether the system is still in the safe state. If the system is in the safe state, you can print out the sequence of processes that can complete their execution within the available resources. However, on the other hand, if you are unable to find any sequence, then you can declare that the system will move to an unsafe state once this request is granted. So you will decline this request. I would suggest to please stop your lecture over here and move on to complete this exercise. Only resume it once you have done it yourself. All right, students, so over here we have a sequence, which means that this request can be granted. So you can see that the new availability becomes 2, 3, 0. And we have a sequence with P1, P3, P4, P0, and P2 that declares that the system will remain in the safe state and this request can be granted. Moving on, let's have another exercise. What will happen if process P4 requests for 3 instances of A, 3 instances of B, and 0 instance of C in the current system after the allocation of the previous request 102 by P1? So the current state of the system is this. What will happen if in the current system we have a request by P4 for 3, 3, 0. So once again, please stop your lecture over here, do your exercise and come back only once you are done. So this was spontaneous. I hope that most of you have figured it out instantly that 3 instances of A is not possible if we have only 2 instances available. So this request cannot be granted. All right, so we have another request by P0 of 0 instance of A, 2 instances of B, and 0 instance of C. Please do it as your homework. All right, students, so that is all for Banker's algorithm. I hope now you can see the big picture where we have prevention, then we have avoidance, and in avoidance we again had resource allocation graph as well as the Banker's algorithm. Now we have the third broader method of deadlock handling, and that is recovery. In recovery, we usually have two major components. The first one is detection of a deadlock, and the second one is the recovery mechanism. In detection, we usually have some algorithm that is executed after a while, which detects whether there is a deadlock present in a system or not. Once a deadlock is detected, then we perform a recovery through this deadlock to return the system into a safe state. This method allows the system to enter into a deadlock state, and then a detection algorithm is in place that executes after some time, and once a deadlock is detected, we have a mechanism for recovery from it. So for the detection, we will discuss wait for graph, and for the recovery, we have a intuitive process of process determination. In the wait for graph, we see if multiple processes are in waiting for each other, and in recovery process termination, we see how can we terminate processes, what could be the order of their termination so that we can recover from this deadlock. The first component is the wait for graph, which is similar to the resource allocation graph we discussed in the avoidance phase. Similar to that, it reflects dependency of processes on each other, and it is only applicable when we have single instance of each resource type. An algorithm is implemented in the system which is periodically invoked after some time to see whether there is a deadlock or there is a cycle in the system. If there is a cycle, it detects a deadlock and calls for a recovery scheme. Over here, we have a resource allocation graph and its corresponding wait for graph. As you can see that in the resource allocation graph, we have resources as well as processes. However, in the wait for graph, we only have processes, but they are similar in nature because the dependency among multiple processes through a resource is reflected in the wait for graph directly. So you can see, for instance, over here we have a dependency of P2 on P3 through R4. So the same dependency is reflected over here by a single edge. So the wait for graph is quite similar to the resource allocation graph. So once we detect the presence of a cycle or a deadlock in the system, we can move on to its recovery. So an intuitive way to recover from a deadlock is process termination, where we terminate some processes to ensure that the system recovers from the deadlock. So there are two basic methods. The first one is if we abort all the processes that are involved in the deadlock to recover from the deadlock. By having this abortion of all the processes that are involved in the deadlock may have several efficiency constraints that are quite intuitive. So we move on to the second method that is a bit more efficient, where instead of aborting all the processes at once, we move on to termination of one process at a time. So we terminate processes one by one until the deadlock is eliminated. So all the processes that are involved in a deadlock, we pick one from them and terminate it and see what effect we get in the whole cycle. If the deadlock cycle is eliminated, then we may move on to the usual performance. However, if the deadlock is still there, we can move on to the next process that is involved in this deadlock and we try to terminate it as well. However, there are also several constraints when we have such mechanism in place. For instance, which process should we choose to terminate? Out of, for example, dozens of processes, which process should be taken as a victim to be terminated? So this is a question that again requires further elaboration. Usually we have priority of process, the already elapsed time of a process, the number of resources it has consumed, or the number of resources that are still pending. So these are some of the measures or parameters that we consider while we are terminating a process that involves in a deadlock. So this selection of a process to be terminated is based on the cost that incurs when we are terminating a process. Once the cycle is broken, the system returns to the safe state and we may restart the processes that we just terminated. However, it is also possible that some process is being selected as a victim process multiple times, which may lead to starvation. All right, students. So that is all for today, as well as from the synchronization section. In this section, we discussed various threading models, then the race condition, as well as critical section problem and some classical problems of synchronization. Also, we discussed deadlocks and some necessary conditions that are important for a deadlock to occur. Then we discussed some methods to handle deadlocks, which include prevention, avoidance, and recovery. In prevention, we try to avoid one of the necessary condition for the deadlock. In avoidance, for single instance of resources, we have the resource allocation graph, while for multiple instances, we have the banker's algorithm. While in the recovery, we have detection and then recovery. In the detection, we have wait for graph, and in recovery, we have a process of process termination. So that is all. So please take good care of yourselves. Thank you.